Hello everyone. In this video, we'll be tackling the question binary search. Now, this is very popular and this is very important because it may be asked in interviews. So it is one of the most fundamental questions that you could go for, and it's marked as easy. It may seem tough at first, but once we're done with this video, you would have the approach in your head for sure. So without further ado, let's understand what they're trying to tell us. So they say that we've been given an array of integers which is sorted in ascending order. Now this is an important detail over here, okay? And they've given us a target, and this target will be part of this array of integers, that is nums. Now, if this target exists, then we have to return the index of that particular number. If we are not able to find it in the array, which is possible, we will return -1. So let's say they've given us this example. Let's bring that over to the board. They've given us this example. The simplest approach is to just go over elements one by one till we find out our target, that is 9. But that is not the point of this question, and if you try to solve it this way, it will most likely not pass at all. The reason is that they've set expectations for us. They've told us that we must write an algorithm which is O log n when it comes to the complexity of it. So linear search, which I just demonstrated, takes big O of n. Alright, it passes through each element once. What we want to do is basically keep reducing our search range so that it takes less time. Basically O of log n time. Alright, so O of log n implies that we have to keep reducing our problem area by half. Alright, so if we are tackling with 4 elements, we want to tackle 2 elements, then 1 element, and then we find our answer. It may sound confusing, but that's basically what binary search means. What do I mean by that? I mean, if I have this array over here, I say that we've been given an important detail, right? That this is sorted in ascending order. That means I could simply drop a pin over any of the elements over here. Let's say this one. If I drop a pin over here, my target, whatever it is, either it will be less than this current element, or it will be greater than this current element because it is sorted, right? So if my target is 9, it has to be ahead of wherever my current pin is. So 3 is less than 9, so 9 has to be in this part of the problem, right? So the binary in binary search implies that we have to keep dividing our problem into parts. So one half and the other half, we have to decide which half do we need to search in, and then we reduce that problem till we are only left with one element. So that's what we have to do. How do we go about it? We start off by taking two pointers. First is, let's call it low. This is at the very beginning. All right, over here. Let's mark it in red. And the other pointer will be high, which will be at the very end. So high would be at the index. Let's just write the indexes down. That would make high as 5. So I say that binary search, the name itself implies that we have to talk about something and divide it into two parts. Binary is what? Zeros and ones, right? One or the other. So we divide this array into two parts. And how do we do it? By dropping a pin on something called a midpoint, right in the middle. So that midpoint is calculated as low plus high. We divide that by 2. So 0 plus 5 is 5. 5 divided by 2 is 2.5. We round it down and go to index number 2 over here. This is our mid for now. So let's write that down. So what will happen now is we will check if our target is equal to the midpoints element, which is 3. So let's just write it as, if this is our array, we check the element at the midpoint in this array, and if the target is equal to that, we simply return mid. Alright, we simply return mid, but that is not the complete solution. But we are getting closer. How? Because now we need to find out which half do we need to search in. So we have mid over here. we can now check if our target is greater than this midpoint element. If that is the case, that simply means that target is in second half. So if target is in second half, we want to make this lower bound of our problem to the element right after mid. I'm just writing it down for now. Low is equal to mid plus 1. Right? So what I basically mean is that we've seen this element, we've already checked it in this condition, right? And we've established that our answer is in this part, not in this part. So we can cancel all this out and our low will be recalculated. But how is our low recalculated? I mean, what all do we have to check over here? So I say that you have to run this in a loop. What will that loop be? We have to keep checking this array till our low and high don't become the same element. Once we reduce our search to just one element, we will know whether we have our answer or not. So there is this, there is this. Question is, what if the target is less than the midpoint element, which is not true in this example for now, but we will still need to handle this case in another examples, right? So if our target is less than the midpoint element, as you can see from over here, the implication is target is in first half, in which case we will lower the right bound to right next to the mid element. So we already have checked mid. We know that the answer is not beyond the mid element, so it has to be in the first half. First half, last element would be mid minus 1. That is where it will be found. All right. So that is what we have to do. So for now, let's zoom out a little bit and try to finish this dry run. So we have over here this part of the array. So we run this loop again and we keep checking. Low, we will be recalculating. It became mid plus 1, right? So mid plus 1 is 3. In the previous iteration, it became 3 and high stays the same. So mid becomes low plus high, that is 3 plus 5 is equal to 8 divided by 2, that will be 4. So this is our midpoint right now. So if this target is equal to mid, which is true in this case, we will simply return our midpoint and that will be our answer, which is 4. And let's see if we are right. As you can see, we are right. But what if I made a small change over here? What if I said that instead of 9, we have 10? I mean, this problem is solved. I want to show you the case where an element is not a part of the array. So let's make this 10 and continue our process, right? So we still have these values. Now we check if low is less than high, and it is. Low is what, 3, high is 5. Target, is it equal to the element at the midpoint? So 9 is not equal to 10. We check the next condition. Is our target, which is 9, greater than element at the midpoint? Again, not true. Is our target less than the array at the element at our midpoint? And that is true because 10 is greater than 9. 9 is less than 10. So high becomes mid minus 1. Mid was 4. So let's rub some of these things over here. So mid was 4. Now high becomes mid minus 1, that is 3. So high becomes 3. Now you can see that these are now equal. So irrespective of whatever mid comes out to be, which will be 3 in this case, low is less than equal to high. This condition satisfies once again. So we go inside. Is our target equal to element at the midpoint? Target is 9, element at the midpoint is 5. Not true. So we move forward. Is target greater than element at the midpoint? That is true because 9 is greater than the element at the midpoint, that is 5. And low then becomes mid plus 1. So mid plus 1 would be 3 plus 1, that is 4 for the next iteration. Now we can do the recalculations over here if we need to, but we know that low is not less than equal to high anymore. It is greater than high now. So we've exited this loop. We did not find our element while we were in the loop. So we will simply return -1 in such a case. So before we move on to the next video where we solve this problem, where we actually code it up, you can try to dry run this particular example to see if this logic works. Alright, so I'll see you in the next one and stay tuned for more.